Oh, recording works.
I have host powers now.
Great. Okay.
So yeah, welcome to the Quantum Seminar, blah, blah, blah. Go ahead.
Good. Yeah. So, and then if we have a little time left, I'll give an outlook how this connects to our core work of 3D lattice clock, how this can be connected one or the other way. In fact, already right now, I would, oops, no, I have to click the key. Yeah. Okay. I would argue that one of the key underlying ideas is really that we want to consider this from the perspective of a joint atom-photon system. Very often in quantum gas physics, for instance, right? We look at Hamiltonians, we consider interactions, and then at the very end, maybe for probing the density distribution, we also shine in light pulses, or we use them as tools to drive whatever Bragg transition. But in principle, it's always two worlds. Like we deal with quantum gases and then use some photons to probe them or drive transitions one or the other way. But this is an example or an experiment where these two aspects are really tightly interconnected. And I think more and more in the future, we will see that this atom-photon interface or the tight connection between the two moves to the foreground. Well, let's look at what all this is about. The key question I want to address in the next half an hour or so is very simple. It's, can we manipulate the natural lifetime of an excited quantum system, right? Like this word, natural lifetime, almost implies when you hear it, oh, that's set by nature. You're given an atom and it happens to have a specific tau for a certain transition, and you can mess around with it, but that lifetime is just set by the atom. And the question is that really true? Well, it didn't take Obama's campaign to come to the conclusion that yes, we can really manipulate that lifetime. Question is how, and well, there is of course many examples that people have come across in the past. There is all these collective effects, right? We often talk about superradiance, subradiance, or radiation trapping. So obviously, if you have many emitters close to each other, they can form, well, let's say, constructive or destructive interference between individual emitters. This can inhibit or enhance radiation processes. So clearly there is a pathway in a multi-emitter configuration to affect the lifetime of the ensemble. There's also well-known experiments that, and these days exploited particularly in nanophotonics, a Purcell effect. Once you mess around with the, let's call it photonic vacuum, you can certainly, by tuning resonators, probably enhance or inhibit spontaneous emission. There's all the, well, of course, the Purcell proposal, and then later all these experiments, like for instance, in Dan Kleppner's group, they really nicely proposed and demonstrated that you can inhibit spontaneous emission if you design a proper resonator around your atom. Yeah, let's look at this a little more systematically. Apparently, you just have to consult Fermi's golden rule. The spontaneous decay requires that final modes are available, right? The photon that gets emitted needs some mode that it can occupy, and the same is true for the atoms. So on the left, you see my little illustration. A properly designed cavity can inhibit that spontaneous emission process. But as I mentioned before, Fermi's golden rule says, well, the rate, the transition rate that you expect is, of course, depending on the internal property, the matrix element of the transition squared, right? But then also the density of states, the available final modes for the system. And then of course, there's this, let's call it Lamp-Dicke factor, which is relevant if you have tight confinement. You have also motional states, and there's a corresponding matrix element there. So looking at this, it becomes obvious that we can apparently mess around with the rate if we start to change this density of state in a very similar fashion as we do with the photons. In fact, once we had the ability to create degenerate Fermi gases, it was really clear that if you embed, let's say in this thought experiment, your single excited atom into a bath of ground state atoms. Let's for a moment pretend it's a two-level system. It's a perfect quantum degenerate Fermi gas, and you have this sort of single excited atom. Well, if we take what we just discussed seriously, then it means all the possible momentum states that decaying atom can reach. And these are pretty finite given just by the recoil momentum. If all these are already occupied in a quantum degenerate Fermi gas by other atoms, then, well, the atom can't decay. All available states are taken. Correspondingly, that little prefactor becomes zero, and the decay rate will be slowed down dramatically. Well, having sketched that idea very in a hand-waving way, let's look a little more in detail at our system. I'm talking about a confined Fermi gas right now. It's for our purposes can be non-interacting. It's, let's say, in a harmonic trap. Then a few energy scales become relevant, right? There is most prominently, of course, the Fermi energy in our system, scales in 3 dimensions, like here with the particle number. What else is relevant? Well, I mentioned there's a recoil energy. If I create one excited atom, it'll decay and it will acquire a new momentum state. There's a corresponding energy scale from that recoil. And then, of course, the temperature, kBT in the system, and confinement. We have given h bar omega. Okay, so in that little illustration, you see what the key point of a degenerate Fermi gas is. Each harmonic oscillator state, for simplicity drawn in 1 dimension here, is occupied, right? And from Pauli exclusion principle, we know it can only be 1 or 0. You can't have 2 identical fermions at the same quantum state. So, well, that obviously means this is not a completely degenerate gas. We're at finite temperature. We have a few holes below the Fermi energy. These one drawn at the very bottom is now going to decay, and apparently in this picture, this decay process can happen. Yeah. Energy that it gets, the corresponding momentum, leads to a place or a level that is not occupied right now. And now, already looking at this picture, it's clear what criteria we have to fulfill to either see an effect in terms of Pauli blocking or not, right? Apparently the ratio between recoil energy and Fermi energy needs to be properly adjusted. If our Fermi energy is way larger than the recoil energy, then this process can be blocked. Otherwise, the atom just ends up in a state that is not occupied, and therefore the process is not blocked. In fact, this becomes a little more obvious when we look in momentum space, as I just said, right? For simplicity, I draw our excited atom now at the 0 momentum to start with. In reality, of course, every atom in that Fermi sea can be the initial one. But for a second, let's assume that we have that one at 0, 0, or in 3 dimensions, yeah, at 0, 0, 0 momentum state. We have an incoming photon. That's just our beam that we shine in. Let's say we start with all atoms in the ground state. We happen to excite the one in the very center of the Fermi sea with the incoming photon, and now it can decay. Well, it's a spontaneous process, so we don't know which k vector it will take. Can go anywhere, of course, depending on polarization and so on. There's a certain pattern, but in principle, emission can happen into the full solid angle. Yeah, so we pick a particular example here. This creates an angle alpha between the absorption and emission vector, and correspondingly, there's a net momentum transfer k in this image. And that defines, as I just described, if this process is allowed or not. Right? In this case, K ends up to be very similar to KF, and also happens to be a hole there. So here we see a process that could work. The atom gets transferred to this other, right now, empty momentum space, and the photon, of course, gets emitted into the corresponding direction given by that vector diagram.
Christian,
and again,
could I ask a question? In this case, where it's a free gas, what you say is fine. But in the previous picture where you had it trapped, then of course we have the sort of thing you mentioned before, Lamb-Dickey effects. You have the trap can take up the momentum. You could have recoilless emission. So it seems like it's a bit more complicated. That is, we don't really have conservation of momentum in the case of the trapped gas.
Yeah, that's certainly true. In the trapped gas, right, particularly the harmonically trapped gas, the situation is a little different. I like to think about, like in this context, really in terms of the local density approximation. So locally in your trapped gas, you can say, okay, here my system is homogeneous with a given density, and here other spot there's a different density. So the local Fermi energy is of course also different, and that will give rise to an inhomogeneity in this effect. That is not visible right now, but that I will actually talk about a little later when I look at a spatially resolved signature in a harmonically confined gas. So we'll come to that aspect. With that idea, hopefully now making sense, let me just point out that it has been around for quite a while. I have a list here of many proposals that people came up with over time, trying to point out that this effect has various consequences, coming up with various configurations. What I have been talking about right now is in a 3D gas, right? It's weak confinement. What I have in mind, weak in the sense that we are not deep in the Lamb-Dickey regime. It's really like a typical 3D quantum gas experiment. We don't have resolved oscillator levels. And there have been other proposals looking at this in a lattice, tightly confined, 2 atoms per lattice side, all kinds of ideas. Yeah, I think here, this actually the 1991, that's one of the very first proposals I'm aware of. Has been around for a long time. So far, no experimental evidence has been observed, even though people have made various attempts. So let me describe what we tried. As you know, our experiment here, JILA, is a strontium quantum gas experiment. We like the strontium atom for various reasons, but most of all because it has this beautiful clock transition at 698 nanometers that can be exploited to do incredibly precise frequency measurements. It comes with a few other advantages. It has, if you want, a narrow cooling transition, what is labeled red mod here. It has a usual broad dipole allowed transition for a blue mod in that case. Various other useful transitions. And in the context of this work, we had various strategies. And let me just describe the first one so that you can get an idea about the challenges that really kick in once you go down this road. The first idea to engineer this Pauli blocking scenario was to exploit this red mod transition. Our idea was really, let me show you this diagram, was really given that this line width, national line width 7.5 kilohertz corresponds to a lifetime of 21 microseconds. So we thought we take this very much one-to-one. We come up with ways to excite, well, first create a Fermi sea, and then excite the atom in there, and then really measure how long it takes to repopulate the ground state. This way, we're hoping to see if the Fermi sea, the surrounding Fermi sea, has the right properties, that reappearance of atoms in the ground state should either be 21 microseconds or slower. Very simple plan. In fact, with the nuclear spin and the ground state properties of strontium, we typically end up really populating 10 ground states. The F equal 9.5 state has 10 MF states. And so as indicated here, we have from minus 9.5 to plus 9.5, all these MF states, 10 of them. So it's like 10 parallel Fermi Cs. And this gives rise to a tempting configuration. We, let's say, just populate the two outermost ones, the 7.5 and 9.5. And then what I've drawn here in this little inset is the Clebsch-Gordon coefficients. Yeah. If we, let's say, go to the excited 11.5 manifold and then this MF 9.5 state, well, it can decay along two directions. Mostly partial width is very high into the 7.5, and of course a small fraction, 0.18 is the Clebsch-Gordon coefficient squared, comes back to the initial 9.5 state. So what we had in mind, the key point of the strategy was, let's prepare an imbalanced 7.5, 9.5 Fermi C. Let's make sure that 7.5 is the majority. Most of the atoms are in the 7.5 state, so that we fulfill this criterion that I had touched on before. The Fermi energy is close to or even higher than the recoil energy for the 7.5. And then we have very few atoms in the 9.5 state. We kind of excite all of them in a coherent fashion, let's say, with an actual pipe pulse, yeah? So that we completely invert the 9.5 population up here. And then, well, given these Clebsch-Gordon coefficients, obviously atoms can decay back to the 9.5. There's nothing left in 9.5, so that process shouldn't be blocked. But this one here, this decay channel should be blocked because these guys here, the 7.5 manifold is full with ground state atoms. So, with a little bit of frequency engineering, pulse configurations, pulse shaping, this all seemed rather straightforward. But in reality, what we ended up measuring in this experiment were lifetimes, like repopulation times all over the place. We could see very short ones, like 8 microseconds, 7 microseconds. We could see very long ones, 30 microseconds, 35 microseconds, at Fermi gas temperatures that are way above any blockade. I haven't mentioned this very explicitly before, but you saw in the images, like in the oscillator levels, also in the momentum space picture, the holes, right? And the hole density is really a function of the temperature. If your temperature is way, way, way below the Fermi temperature, then this hole density is very low. Correspondingly, the blockade is very pronounced. If you approach TF, then really you don't expect much of a blockade. And we did this experiment in the setting I just described, and nevertheless we saw any lifetime we wanted. Sometimes it was very sensitive to some parameters, like the ratio of the 9.5 and 7.5 manifold occupation. Sometimes you could go to very high temperatures, wouldn't change anything. So clearly there's more going on than the simple picture I just described. And indeed, I've mentioned this already, all these effects, these other effects that can mess around with your lifetime really kick in, right? It's not too surprising if you have this dense ensemble of emitters close in terms of a comparison to the wavelength. You can have all these things that people have described in the past as multiple scattering, radiation trapping. In fact, we then really looked at what was going on. You could see you drive this excitation. The atoms get to the excited state, you extinguish your drive pulse. Of course, that is timed to be shorter than the expected lifetime, let's say 3 microseconds or so. Turn it off, and then what you actually see is that the cloud really emits a directional flash along the drive pulse direction. So the perfect example of a coherent process where all your emitters are phased in to re-emit into that we'll call it super radiant direction. There's subtle differences. Now you can argue if you do a perfect pipe pulse, you don't imprint phase information. So the system first has to rephase to re-emit into a given direction. And it's actually beautiful physics. We can observe if we deviate from a pipe pulse so that coherence is imprinted into the sample. You see that the decay typically is faster. You don't have this build-up period. It's always directional in the very same imprinted direction. So the noise shot to shot is lower. If you go pi pulse, the noise is higher, but often you still, pi pulse is not perfect, so you're still preferentially emitting in that direction. Long story short, this first appealing but very simple approach didn't work. So let's revisit our strontium atom here. First approach was a coherent resonant drive. We had this engineered imbalance between two Fermi seas, and we were detecting ground state atoms. Well, one standard recipe if you have trouble with density is go detuned, right? Go to the weak excitation limit. In our strontium, we switched to the blue transition, 32 megahertz, so we're talking 5 nanoseconds. Can't easily resolve that anymore in terms of a population measurement, but of course we can always detect the scattering of photons in a certain direction. We're now dealing with 10 balanced Fermi seas. Doesn't matter for the physics, but it's nice and advantageous because we get the signal times 10, because this happens then in every of the 10 Fermi seas in parallel. As I said, the idea is now to use a weak drive of that transition, shine in light off resonantly for a time way longer than the decay time, and watch the emission of the photons. We illustrate this a little better in this picture. We have our Fermi gas here, like these little red atoms in a horizontally more tightly confined trap. We shine in this blue probe, and then given the parameters that I've plotted up there, you see our Fermi energy is on order recoil. We reach temperatures down to 0.1 of the Fermi temperature. And then as we shine in this pulse, we collect scattered photons along two directions. One is at 24 degrees with respect to the drive beam, the other one at 72 degrees. Because there are certain NAs, they're different for the two directions. This has consequences for signal to noise. But in principle, as you can see in these two Fermi sea diagrams, we're probing two scenarios, right? At this shallow angle of 24 degrees, the effective K vector is rather small compared to the Fermi vector in our system. So most of the time, now talking about the central density of the cloud, most of the time we'll end up within the Fermi sea, whereas in the other case, vector sum is such that final momentum state will mostly be outside the radius of the Fermi sea. So far, so good. Driving this, of course, well, if we don't want to destroy the effect we are looking for, it's obvious that we need to be very conservative in the number of photons or the number of scattering events we drive. After all, if we shine in light for so long that so much momentum is transferred that the Fermi sea is destroyed, then we'll can no longer hope to observe suppression. In fact, can give this challenge in a more quantitative way. We want a high Fermi energy for the reason I have already described. Well, in a three-dimensional gas, that's coupled inevitably to a high optical density. And optical density is really a key parameter that decides whether you are bothered by all these collective effects. And I mean that in a very broad sense, or not. Yeah. Optical density is really just the integrated column, like the column density integrated along line of sight. So two things enter your absorption cross section right here on resonance, roughly lambda squared, and if you want the radius of the atom for radiation, and then the Fermi energy is directly connected to your density. So then if you look at these two quantities, then it's clear if you want this criterion Kf larger Kr fulfilled, then you end up having an OD that is appreciably higher than 1. And that, as we have already seen, brings you back in this regime where you have to worry about all these challenges. In fact, it's very obvious. If we drive our transition in the scenario I described on resonance, what we see when we have a camera along the direction where we collect the photons. We can spatially resolve it. We see a ring, right? We have a cloud with the highest density in the center. The image that we observe is a ring. Well, that again tells us we're really in this regime of a high optical density. We see the ring because the atoms in the outer rim of the cloud scatter light, and that light doesn't need to travel through a thick, dense optical density. So you see it, whereas the one in the center, where more photons are scattered, has to travel through the thick part that is like the opposite side of the cloud. So effectively, the signal from the center gets heavily attenuated. Once we detune far away, this effect is taken care of, and the image we get, although weaker, represents the proper density distribution.
Sorry, that's the fluorescence image.
Yeah, it's a fluorescence image, exactly. Okay. That's right. It's really the idea of the experiment, as I said, is to collect the photons that are emitted along a certain direction. Good. So, long story short, apparently far detuning is helpful. We want, as I said before, a weak excitation regime, right? We want to excite just very few of the atoms that we have there to not destroy the Fermi sea. And then we want to play a few more tricks. The superradiance is a complicated process. It not just depends on the optical densities, other parameters contribute. We'll try to play a few tricks that lead to common mode suppression. So even if we have superradiance and other effects, collective effects going on, we try to run the experiment in a way that there's some common mode suppression of these effects, and we have a differential readout for what is really coming from the, let's say, Fermi statistics or quantum contribution. Let's get a more precise idea about the suppression we expect in this experiment. Coming back to the very initial Fermi's golden rule, right? We can really write down the suppression factor more or less in a straightforward fashion. We have an initial occupation number for each state in our Fermi gas system, and then there's a final one. And if the final one is fully occupied, 1, then of course this process can't happen. And then this normalization, we directly get the suppression ratio as a function of Fermi gas parameters with this equation. We can calculate it. I've plotted two sort of scenarios. The left, which is corresponding to our parameter set, Fermi energy and recoil energy being pretty similar. And then you see, as we shine in a photon along the given direction, depending on the effective momentum transfer, the emission is more suppressed. Like in the forward direction, net momentum transfer is almost 0. So the strong suppression, we end up within the Fermi sea. But then as we go outside, we end up outside the Fermi sea, correspondingly very weak suppression of axis in this case. If our Fermi energy...
Just for, I mean, like it's of course stupid, but I mean, just for compare, big suppression here is small emission, or? Yeah,
that's right. What suppression means is always a little confusing. It's really meant that 1.0 is no suppression whatsoever, right? So multiply, basically you can say we're looking at the differential scattering cross section, and the suppression factor is 1 if there's no suppression, and more suppression means it gets closer and closer to 0. Yeah.
Okay, so
in the question, I'm a little bit confused here, though. It seems to me that if I have perfectly forward scattering, then I end up in the state that I started with, and that shouldn't be suppressed because that state is available.
That's correct. So the very perfect forward scattering, that's really, let's put a little plug there, or let's assume for a second that the perfect forward scattering is sort of the process where you really stay coherent, or where you never leave your state, right? Because you come exactly back where you started. Let's ignore that for a moment. Okay. That's really because, as I showed, right, the detection, we do detection either at 24 degrees or at close to 72, 74 degrees. So we are never really probing this straightforward direction.
Yeah, right, but But thinking about this picture, it seems like there should be a brighter spot right on the axis, and I'm not sure. Maybe it's as broad as some diffraction limit or something.
Exactly. Yeah. You would, depending on the size of the cloud, right? You have a corresponding diffraction limit that you would expect. But let's say that's planked off, right? It's
okay.
Sort of hidden here. Yeah, that's right. Okay, so let's just look one more time at the momentum space. Using the expression I've given before, we can now nicely parameterize this. We can really plot what we expect. It's a semi-classical calculation, very simple. And you can see here, strong scaling with the temperature as we expected. As we go more and more degenerate, the suppression gets more and more pronounced. And of course, we'll also scale with the ratio momentum transfer versus Fermi momentum. If the net momentum transfer is low, suppression gets correspondingly more and more pronounced. So far, so good. Now you see these little lines here. That's where we explored our system. We kind of change parameters, either temperature or confinement, and accordingly Fermi energy and KF. And we're looking at the number of photons that we could detect along the two directions. And as we were hoping, we could really see a suppression that is kind of following the theoretical prediction for the two scenarios. Again, I'm plotting the 72-degree case in red and the 24-degree case in blue. Yeah, 24-degree smaller momentum transfer. You expect a more pronounced suppression. And indeed, as you lower temperature here, keep everything else constant, you see that the number of photons we detect along that direction comes down. Whereas the other direction stays constant, maybe comes down a tiny little bit, kind of in agreement with what you quantitatively can calculate. Similarly, changing confinement, accordingly Fermi energy, keeping temperature constant. We also observed that in this case, some more pronounced dependence, and here, yeah, there's also some deviation, but it's kind of staying in the close to not being suppressed. I should now, well, we see this nice agreement and think, wow, it's all there, right? But who knows? From our strategy one, we have learned that one has to be really careful. So I'll quickly describe how we play a few tricks and do some common mode suppression or checks that convince us. A Fermi C is a delicate thing, right? If you heat it up a little bit, if you poke holes one or the other way, it's gone, it's destroyed. So we actually do this in order to figure out if our effect is real and really related to quantum statistics. This pulse that we shine in to probe, a microsecond pulse, is still very long compared to the natural lifetime, right? It's this weak CW drive limit. What we can do is we just fire a more intense pulse a little bit before the actual probe pulse. If we scatter sufficient number of photons, then each atom will get a few momentum kicks, 1, 2, whatever, sufficient to really poke holes into this Fermi C. Yeah? And accordingly, if we time this properly, we can do it such that the density doesn't really change after applying that pulse and just waiting 10 microseconds. Right? The momentum kick is not such that the atoms fly apart in that 10 microseconds. On the other hand, it certainly is sufficiently long to end up with a state that has a way wider momentum distribution, no quantum degeneracy anymore. And then we just run this experiment in the two scenarios, either with or without that pre-pulse, and measure how the during the probe-pulse detected photon number changes, now along this shallow angle. And then we observe, oh, if we go to a high temperature Fermi gas and change that pre-pulse duration, signal kind of stays constant, whereas we start degenerate, then we really see, as we make that pre-pulse longer, the counts that we observe get up to well, this in this plot to the thermal limit. So really, as we destroy the Fermi C, we see that the scattering signal gets enhanced. And as a little further evidence, there is the possibility in our experiment to spatially resolve the signal. As we were discussing before, our gas is harmonically confined. So to some extent, in a single run of the experiment, right, we probe different K over KF ratios. We have the region in the center of the cloud where the density is high, correspondingly high Fermi energy. We have the region outside where this Fermi energy is lower, density is lower, and therefore, in relative terms, the suppression outside should be way weaker than inside. So it's pretty tricky because the number of photons we scatter is supposed to be very low. And if we now start to spatially resolve them, as you can see in this image, we're really talking about detecting on a mean photon signal of less than a photon per pixel. So we average tons of images, 1,000 images or so. We're lucky because our experiment is fairly stable, so things don't move around. We can really stack up these images, average them, and then look at the spatial distribution of the scattering signal. We get these blue data points. And then, well, we go through a process to independently measure the density distribution. We can just go to the super high intensity fluorescence imaging limit, get a density distribution, at a calibrated atom count. So we can really calculate, or indirectly, let's say, measure the signal we expect for this cloud to see in a not Pauli plotted scenario. That's this purple trace. And then we can also calculate, given the expressions I've shown before, how the spatially resolved Pauli scattering intensity should look like. That's this blue curve here. As you can see, obviously the data points nicely follow what we expect, except in the very center of the cloud. It's very well possible there's a little, still some collective effects kicking in. So far, so good. So I think I've shown you, you can really observe a signal where you have a suppression of scattering, of light scattering, as you approach quantum degeneracy. I've introduced this factor S, a suppression factor. And in the remaining 5 minutes, I want to point out that that is not just a suppression factor. It's actually related, or it's more or less, it's directly a quantity that is well known in describing any sort of many particle system. It's the static structure factor. That's really what we are measuring. It's a different language, but you will see it creates some nice connection. It's actually beautiful physics connecting three different things that at first sight seem to be very separate. Let me just say, we're looking at, as I described before, you can really think about this, particularly strategy 2 as a measurement of like a scattering experiment, and we measure a differential scattering cross section. And from Fourier's theorem, or from playing with diffraction gratings, we know that there's this correlation, this connection between having scattering along a certain wave vector, and density modulation in your system. Now we are really thinking this picture. You have individual driven atoms, all of them in a coherent way. That there is basically a number of point scatterers that are arranged in space. We drive them. We're in the weak drive limit. It's all nice and coherent. So we can think of each of these driven atoms as little emitters, antennas that all contribute in the far field. And then, well, as drawn here for diffraction grating, you can connect the density modulation or the characteristic 2 pi over that distance to the momentum transfer. And it's really that a scattering event with that momentum transfer Q requires a density modulation at that same wave vector. To make this point a little clearer, let's look at some distribution here. It looks pretty ordered, like a crystal. Can be any other distribution where the atoms are pinned to certain points in space. As I said, let's think about a weak drive limit. There's a coherent response of the atoms. We have a detector under a certain angle with respect to that drive pulse. And now we are asking, well, what are we seeing in that detector? Using this very simple antenna picture, well, our argument will be total atom numbers. And let's, in a thought experiment, say we distribute this region now into little subvolumes, right? Those that contribute an in-phase signal to the detector, and those that contribute an opposite phase signal to the detector. So if I sum them up, I will have N+ atoms in the in-phase regions and N- in the opposite phase regions, just to sort them. Here, I've drawn 2 volumes, but in reality, of course, you'll have many different regions, either in or out of phase, not just 2, the spacing between the atoms, maybe on the order of the wavelength. So you really have to do a fine cluster of different regions. A bottom line in this coherent scenario, the detector signal is basically the difference, right? The difference squared. Light and intensity, the emission is, the process is linear in electric fields, so in intensity we expect N+ N1 squared times the signal from a single atom. And then if we have a system with thermal distribution, we have a binomial distribution to be either in the N+ or N- regions. If you put all this together, you'll arrive at the very intuitive result that your scattering along that direction is just N times the scattering of a single atom, if you have random distribution. However, by the very same argument, if you have balanced N+ and - contributions, you'd really say, no, a perfect crystal can scatter no light. It's just what we discussed a few minutes ago. You have destructive interference everywhere, except in the forward direction. So I hope I have illuminated this aspect of this connection between the density fluctuations in your system and the corresponding scattering cross-section. There is a formal language to put this in, right? I was saying before, this SK can also be really one-to-one interpreted as the static structure factor of the Fermi gas. And that's defined as the Fourier transform of the spatial density correlation, right? It's this expression given down here. So if you do the Fourier transform, you get the structure factor. If you run this correlation calculated for Fermi gas, you arrive at this expression for your structure factor. And that's exactly the expression that you get when you calculated the suppression factor in the sort of occupation number argument I was describing before. So clearly, there's this connection between the suppression of light scattering and the suppression of density fluctuations. And that connection goes even further. If you have a system that has intrinsically suppressed density fluctuations, it's actually connected through the, call it fluctuation dissipation theorem, to the compressibility in the system. If your fluctuations are thermally driven, then really your compressibility connects to the relative fluctuations. If you just say, I pick a small subvolume in my gas and look at the density fluctuations with respect to the mean density that I expect there, those will be connected to the isothermal compressibility. For classical thermal gas, you will always recover Poisson fluctuation. So dn over n, that squared over n, that ratio is going to be 1. However, for Fermi gas, compressibility is different. It's such that you end up seeing that delta n squared over n is suppressed as you reach degeneracy in the very same fashion that light scattering gets suppressed. So all these 3 aspects are interconnected. And last slide, the suppression of density fluctuations in a Fermi gas. Actually, at the beginning of my PhD, we observed that for the first time. And now, maybe 10 years later, we have really closed that loop and finally also localized the effect in the, let's say, photon domain. So here is that old paper where we illustrated, for hot gas, N and the variance of N are pretty similar. It's not perfect here because hot was not as hot as a thermal gas should be. And in the cold case, quantum degenerate, you saw that these density fluctuations were reduced compared to what you expect from a full thermal fluctuations. So this creates the connection between all three aspects that I had mentioned before. Maybe that's a nice round story and a good point to stop. As I was saying, I could tell you a little bit how this connects to 3D clockwork, but I think if there are questions in that context, I'm happy to talk about it. But for now, I'll just skip the 3D clock stuff, give you very quickly the conclusions. We saw the Pauli suppression of light scattering of the quantum degenerate Fermi gas. This is really interesting because it gives us a new tool, right, to quantum engineer these atom-light interactions. If we embed our atoms in a Fermi sea, apparently that does something to this atom-photon interactions. We can think about engineering that lifetime, which is interesting for clocks in a longer run. If you have a clock atom and you're unhappy because your excited state decays too quickly, well, maybe you can engineer it into a sub-radiant state one or the other way, effectively enjoy a longer lifetime, presumably make a better clock from this. And at the end, these collective effects that have been bothering us in various ways here, they are also very relevant for clocks. After all, our goal is a high density array of emitters. So even on a clock transition with an incredibly small line width, they will eventually kick in, maybe not in a dissipative fashion, but in a dispersive fashion. So there will be frequency shifts associated with these tiny dipole moments that will pretty soon become relevant for super high precision optical clocks. All right, a few references. I didn't put them in the individual slides. And finally, this is the team that has been doing all the work in Junier's lab, a 3D lattice clock team. With that, thank you very much for your attention.
I'm showing a clapping hand smiley and also the tada, the representation of celebrating your nice talk. Thanks a lot for this. I'm sure there are quite a few questions. If you have questions, raise your hands or just ask them. I think we're well, up to you. You can also write them in the chat if you want. I can start if there are. I mean, I see Dima is already ready to ask a question, but normally he also raises his hand. So I'm going to start. So you pitched it with changing the natural line width. Did you measure the natural line width at all, or could you extend your measurement to do that?
Yeah, that's really a key question, right? Because initially I was setting up and saying, oh, look at the lifetime, think about this in context of the lifetime. And the first approach on the red transition was very much in that spirit. As you saw later, the trick we played was to have directional detection, right? If we say we detect along a certain angle, then of course we kind of make a pre-selection of the momentum states we worry about. If that is a very shallow angle, we can only detect those scattered with small momentum transfer. And that means that if we are now talking about tau or the associated tau that we expect in that scenario, then that suppression will be rather small, because there we can we have the full 4 pi solid angle, so that decay is not necessarily suppressed in all directions if our Fermi energy is not extremely high compared to the recall energy. So indeed, if you calculate for the given scenario that I described, given parameters, the the total change in lifetime that you expect would be on the order of 10%. So it's a small effect, and given the lifetime of 5 nanoseconds, we didn't resolve this in the spirit of what I call strategy 1. So we didn't watch a sort of call it a strong drive response, right? It was a continuous drive, and we were really looking at the rate and not at the decay itself.
Yeah, thanks. You want to read it?
No, it's everybody can see it already.
Should I look at the chat?
It's okay. I just said that I didn't think it was possible, but you found the key to immortality apparently.
Well, thank you. Yeah. It's you know, sometimes these, right, there are always these proposals that pop up very early because people think, oh, this is something. Once we have a Fermi gas, this seems very tempting to do. But then, you know, focus moves to other things. But somehow it was always in the background of people's mind, I guess. In fact, back then in Wolfgang Ketteler's group, when we were looking at the density fluctuations, we also had the goal to see this, but back then didn't work out. Lithium, that was the fermion we were using for these density fluctuation measurements. Lithium also doesn't have the best properties in this context, right? The mass is very light. So your goal to reach a Fermi energy that is sufficiently high is not so easy to reach. Although, as I mentioned, Wolfgang Ketteler's group has kind of in parallel with our efforts gone down the road of incredibly compressing their Fermi gas, so that even with lithium, they could reach a very high Fermi energy. In fact, the densities are so high that their experiment is really pushing to the regime where EF is way larger than ER.
Thank you. There are more questions. Here, I have to say it. The picture looks photoshopped. Is it?
No, you think all the masks are taken off? No, it's not. It's real.
If it was Photoshop, there would have been Jung Yi on it.
That's correct. Yeah. Yeah.
So it looks photoshopped.
Christian, toward the end of the talk, you talked a little bit about shifts. Whenever you are thinking about clockwork and you try to do something that makes the line width narrower, you always worry whether that same process will cause a shift. And you mentioned a little bit, but could you say a little bit more about how the shifts might come in?
Yeah, absolutely. So let me go to that slide. So, you know, here I was saying, okay, a 3D lattice clock, right, is a scenario where we really create this dense array of atoms. Spacing is given by the magic, like half of the magic wavelength that we're using to confine the atoms. At the end of the day, you can also think of the lattice clock as a scattering experiment. Of course, normally we don't detect the scattered photons. We really just detect ground state populations. However, the general spirit here is if we confine one atom to each lattice site, we get rid of all contact interactions, right? All the interaction terms that normally kick in a gas taken care of. The atoms can't tunnel, they're really frozen, lattice is sufficiently deep. So at first sight, you would say no interactions. Yeah? But then, as I was mentioning, imagine so we use a coherent spectroscopy, right? We excite the atoms. We can maybe send in a pi pulse and then a pi over 2 pulse to do Ramsey spectroscopy, wait a little time, another pi over 2 pulse to read out. So as we do this, we create tiny dipoles, right? The gamma is tiny, correspondingly small dipole moments, but at the end, it's dipole moments. So we all know just from classical physics, if you have an array of dipole moments, there is going to be some long-range interactions. These dipoles see each other, and therefore we can actually calculate what's going on. We can say, let's assume this is an example to directly address your question. What kind of shifts do we expect? This is an example where we say we come in with a pi over 4 pulse. That actually enhances the effect compared to a pi over 2 pulse. So just to set the stage, we take a 10,000 atoms, arrange them in the fashion I had described before. For strontium, it's 813 divided by 2, the spacing between each lattice side. And then theorists can model this with their master equation, right? We have terms for various contributions. At the end, in these interactions, we can like flip excitations. There's crosstalk between different dipoles. But really, for the frequency shifts you see here across the cloud, right? There's a sort of inhomogeneous distribution. Some are shifted maybe 2 millihertz order line with respect to let's say 0 shift scenario. These shifts really in the limit that the experiment is done here, where the Ramsey time is short compared to the line width, in this limit, they're really one-to-one classical picture. So you can really calculate what's the dipole moment. Then you look at EM dipole interactions, and you just integrate that over the duration of the Ramsey time. And then you pretty much see already the frequency shift that is plotted here. And now for actual clock work, right? Normally the readout is done in a not spatially resolved way. So your clock signal or your shift in fringe due to these interaction effects, long-range interaction effects, is of course the mean of the contribution of the atoms. But even the mean is not 0. So indeed, if you operate a clock and you're approaching the limit where you push below the natural line width, there will be shifts associated with these long-range interactions. And it's actually a very fascinating regime, because on the one hand they're super tiny, and you would think no one ever bothers or can measure them. But then again, these instruments, these clocks, are so tuned so precisely. We've taken care of all kinds of other shifts that it should actually be possible to resolve those, right? And then you're really suddenly dealing with a quantum spin system that that has long-range interactions in a limit with very long coherence time and very weak interactions. So it's really then again leaving the clock domain and becoming a quantum spin system that is interesting in its own regards.
Okay, but it sounds like from the story you've just told that the main effect of narrowing the line width is using a long Ramsey time, not really involving the Fermi statistics. That's
correct. The scenario I just described
assumes
that you have started off with 1 atom per lattice side. That's right. Yeah. In another scenario, you could say, well, let me engineer this, right? Let me put now 2 atoms per lattice side. Let me do it such that somehow I manage to have one sitting there and the other one excited. And then, well, the excited one is supposed to decay. But if you have 2 on that very same lattice side, then Fermi statistics will kick in, right? The ground state is occupied by the other atoms. So only channel you have left is was basically scaling with some power of the lamp decay parameter. You only can decay to the excited oscillator state. Yeah. And then yes, then of course you have these on-site challenges. There's interaction terms kicking in. So how can I say, this narrowing that you can get from embedding into a Fermi sea, then in a practical sense, of course, comes with contact interactions again. So it's a longer path.
Yeah. Okay.
Great. Are there more questions? I would advertise next week's seminar. Maybe I can actually in the meantime. But since also that server is down, next week is we don't have anything. There's public holiday in Germany. Praise the Lord. And after that, we have Anna Maria Ray, but I will advertise that during next week's seminar. No, I won't, because there's no seminar. Yes. So one last question from anyone? I ask a question then. So what's next with that machine?
Yeah, what's next is really, as I said, we are very, at the end, our if you want, key competence or ideas are centered around the clock, right? And what we want to do is we want to push for longer and longer coherence times. That makes the clock better and better. We're actually facing a challenge that is not related to what I was talking about. If you confine these atoms with this magic wavelength, there is actually a parasitic scattering going on because you're not infinitely detuned from any other transition. So the lattice light itself tries transitions, in particular the excited state of these clock atoms has a weak rate at which it is sent back to the ground state just off resonantly from the lattice photons. And that process makes it hard if the excited state lifetime in the lattice, in the deep lattice, is limited to, let's say, 15 seconds. You can't profit from this beautiful long lifetime of 120 seconds. So even before reaching the point where we would want to extend the natural lifetime, our first step right now is actually to fully exploit the natural lifetime and not be bothered by the reduction due to the off-resonance scattering from magic wavelength photons. And that's really a tricky game because obvious thing to do, lowering the lattice depth doesn't win you. You eventually start to allow tunneling, and that then of course reduces your coherence time. However, if you want to go to a more shallow lattice and stay at the magic wavelength, the easiest way to do this is to change the lattice spacing. This way, you reduce the tunneling rate. The wider the atoms are spaced apart for a given depth, the lower the tunneling rate. And doing this means you really get to enjoy the full natural lifetime. If you're approaching 4 recoils, then you're not bothered by this off-resonance scattering anymore. And at the same time, spacing, let's say, order 1 or 2 microns, you are you can't tunnel over the time scale of that natural lifetime. So you win in both directions. And on top, if you make the spacing wider, then of course these dipolar effects are also reduced. So the direction, the first step, short answer, is fully exploit the natural lifetime. And then next step will be for actual clockwork to go beyond the natural lifetime.
Great, thanks a lot for the answer and for a great seminar on an interesting topic. Seminar is closed. See you all in 2 weeks then. And we, of course, always happy to have Bill Phillips here, even though he seems to be correlated to speakers from JILA.